welcome into lecture number 16 of Calculus 3. This lecture is on triple integrals. So a triple integral is exactly what it sounds like. It's going to be the obvious extension of a double integral. And I'll write out some details here of how it's going to work. It's hard to visualize geometrically, a little bit harder, I should say, to visualize geometrically than a double integral. But the idea is going to be exactly the same. So let's say that E is a bounded region in R3. So let's let E be a bounded region, and I'll draw a picture of this in a moment. Region in R3, and so this is going to be the domain of the integrand, the function in the integral. And so we're going to then suppose that W is given by some function of x, y, and z. So W is equal to f of x, y, and z, and we want this to be a continuous function. As we know, that's not necessary for integrals, but it's going to be enough, more than enough, right? So a continuous function on this region E. Okay, so then the triple integral is going to be just this symbol, triple integral over E of f of x, y, z dv now. So dv means that we have to take the volume element of the domain space, right? So that's the volume element of the domain space times the output of the function. So this is going to measure then, the volume is a three-dimensional volume, right? What we're used to, three-dimensional volume, times another dimension, which is the height of the function, quote unquote, the height in some sense. So this is going to measure what we can call the four-dimensional volume of the shape enclosed between the graph of the function and the region E in four-dimensional space. And that's why it's hard to think about or visualize geometrically, because four-dimensional space is a space that's really hard to comprehend. We live in three-dimensional space, and it's hard to comprehend what that fourth dimension might be. But anyway, let me write this down. But this now measures what we're going to call the four-dimensional volume of the region enclosed between the graph of f and the space region E, right, whose volume is given, it's a volume, it's a three-dimensional volume, three-dimensional region, so it's got a volume element dv. So the graph of f and E, and this all takes place in four-dimensional space, right? So one way that people have thought of to try to visualize the graph of a function of three dimensions, of three variables, so the output is in the fourth dimension, is by thinking of the function as assigning some color, right? A color, or maybe some other property that you can think of. So you've got your domain in three-dimensional space, and then to every point in that three-dimensional domain, the function assigns a different color, or maybe a temperature or something like that. So again, this is not easy to envision, but because it's in four-dimensional space. But otherwise, the geometry is exactly the same. We can compute this as a Riemann sum. We can write this out as an iterated integral if our region is a rectangular prism, right, like a box. So again, let me draw some pictures here. So our scenario is going to be that we've got our domain space here as some three-dimensional, maybe blob-like region, right? So this will be our region E, and this is going to be our domain of our function. So we've got this region in x, y, z in our three-dimensional space, right? So that's the domain, and this is thought to be a solid region now. Our function is assigning to every point on this region, it's assigning a fourth number, right? A w. And so for every point inside here, we get an output over here, right? And so again, it's hard to put this all together, but somehow the integral is going to measure the four-dimensional volume that's bounded between the graph of this function f and the region E itself. All right, so it's a little bit hard to describe. But like I said, the nice regions that we're going to study, at least in rectangular coordinates, are going to be when our regions E are bounded by, our textbook calls these boxes, so they call the regions B instead of E. So E is our general region, but if this is a box that's bounded in the x, y, and z directions by just intervals, then this is going to be, we're going to be able to iterate this integral, right? So maybe this one goes from A to B in this direction. Maybe the y goes from C to D, and then the z maybe goes from E to F. Maybe I don't really want to use E and F. Let's say from U up to V. And then if this is our region, then our triple integral over this box or rectangular prism region, f of x, y, z, dv. This can be written, this is kind of a Fubini's theorem. So this is a version of Fubini's theorem. But this can be written as an iterated integral in any order that we like, right? But I'm going to write it this way. So I'm going to go from u to v on the outside, from c to d, and then the innermost, I'm going to go from a to b. So this means that my volume differential, the volume of this thing, is going to be change in x, change in y, change in z. So it's going to be dx, dy, dz. All right, and this is the basic idea. And again, this is a very straightforward extension from 2 dimensions to 3 dimensions. All right, so let's see how this works by doing examples. That's going to be the easiest way for us, right? Just do some examples, work them out, and see what we get, see how this all works. So here's the first example. We want to compute the triple integral over region E of the integrand 6xy dv, right? So a volume integral, 3-dimensional integral is always going to be with respect to volume, dv. And then for this to make any sense at all, we need to describe now what this region E is, right? So here's how I'll describe it for this one. But for this one, E is going to lie under, so I'll say it this way. I'll say what it lies under and what it lies above. But it lies under the plane. So I'll give you the plane. The plane's formula is going to be z equals 1 plus x plus y. And it lies above the region in the xy plane. So above the region in the xy plane that is bounded by the following curves. There's going to be 3 curves. It's bounded in the xy plane by the square y equals square root of x, y equals 0, and x equals 1. All right, so this is going to be our region E. That's what we integrate over. The integrand is given to us as 6xy. Let's see if we can get a picture now, sketch a picture of what this region looks like. So x, y, z. It's going to be important to just try to sketch this, right? So let's try to do, I'll do it this way. We'll color code these, okay? So we'll start with this y equals the square root of x. That's the same as x equals y squared, but where x, where x has to be positive, right? So that's going to be the graph that goes this way, right? So I'll try to sketch that in the same color, but that's this one. So this is y equals the square root of x. If you turn this kind of, if you can imagine twisting this so that it looks like your usual xy coordinate axes, that's exactly what the graph would look like, right? Y equals 0, that's the x-axis. And x equals 1 is going to be a vertical line, right? So let's make those different colors. All right, so we go back. Y equals 0, that's our x-axis, so it's like this. And then the last part of this is going to cut off a region here, right? A bounded region is going to be this one. So we'll just say this is x equals 1 right here. So now we know that our region lies above this plane region right here, right? It lies above the plane region, but this is not a solid region yet. The last thing we need to do is figure out what role our plane plays, right? So this one has a z-intercept of 1, and then it increases in both the x and the y directions with a slope of 1, right? So again, I'll try to sketch this over here, but at this point, let's say this is z equals 1, and then this plane is going to have a slope that kind of goes up like this in both cases. So here's the plane, but now the region is going to be, and again, it's hard to visualize. This is 3-dimensional, and I'm not the greatest drawer, but the idea here is that now we've got this portion here, and then we're going to trace along this, right? So up here we get this curved region, and then straight over to here and down. And so this is supposed to look like some kind of a wedge shape, right? Some kind of a wedge that travels along directly above this region down below, and then it travels up to here, and then we have this solid region. All right, so that's kind of for this example, that's going to be a lot of the hard work. We're going to have to do some computation here, but a lot of the hard work is just figuring out what the region is, right? Now we need to integrate over this region. This is not a rectangular prism, but we can treat this like the type 1 and type 2 integrals that we studied for double integrals. And because of the way that this was described to us and the way that we've sketched it, it's pretty clear that we're going to want to integrate in the z direction first, right? So in the z direction, what are the bounds of this region? Well, the lower bound is the xy plane. That's z equals 0. And then the solid goes up to, in the z direction, right? It goes from the xy plane up to this plane that we've just, I've poorly sketched. Hopefully you did a better job, but this plane that's been sketched right here, right? So this green plane, and that's the equation. The equation of that one is 1 plus x plus y. So our inner integral is going to be, with respect to z, it's going to be bounded from 0 up to here, right? Then what do we have to do? Well, then we have to integrate the rest of this on the floor, right? Because once you integrate out the z direction, you're going to be left with just the xy coordinates left over. And so then we need to integrate this one. And this one can be done as either a type 1 or a type 2. Doesn't matter. So I think probably the best way here for us to do this is to go in the in the x direction first, right? Go parallel to the x direction and collapse everything to the y. It doesn't matter. You can do this either way. But I'm going to do it that way. So I'm going to say, all right, the next thing that's going to happen is our x is going to go from what looks like a parabola here, so from y squared, up to x equals 1. So in this direction, right, as it goes this direction, as we integrate in this direction, it's from the parabola to x equals 1. And then at the very end, our last curve here is just going to, this is all, once you do that, right, then this all collapses down to this interval. And this just goes now from 0 to 1 in the y direction, right? So y is going to go from 0 to 1. And so at this point, we can write out our integral. So our integral, this integral right here, we need to write out the bounds. That's the key, right? The integrand itself is 6 times x times y. So let's write this out. So again, we're doing triple integral over this region E that we were given of 6xy dv. We're going to replace that by inner integral 0 to 1 plus x plus y. 6xy is still the integrand. This is times dz. Next integral out is going to be in the x direction. It's going to go from y squared up to 1. All right, and that's going to be dx. And then finally, we'll finish this off with the integral from 0 to 1 dy. And so this is what needs to be computed now. Okay, so that's what we'll compute. This is not, it's kind of separable to some extent, but not really, right? Because it's got these functions in the boundary. So let's not separate it at all. Let's just start on the inside and work our way out. So we'll have integral from 0 to 1, integral from y squared to 1. Those stay there. And then on the inside, we integrate. This is just constant with respect to z. So this ends up being 6xyz. And then as z varies from 0 to 1 plus x plus y. And this is all the inner integral, right? And so we just carefully work this one out. When we plug this in, that's going to go in for z. And then we'll get this next term here, right? So then our outer integral is still 0 to 1. Then we're going to have y squared to 1. When we plug this in, this is going to be 6xy plus 6x squared y plus 6xy squared. That one's going to be dx first, right? And then dy. Okay, so we work this one out again. 0 to 1. Antiderivative here. This is all with respect to x now. So this one's going to be 3x squared y plus 2x cubed y plus 3x squared y squared. And for this one, we're going to plug in x equals y squared and then up to 1. All right, so we have to very carefully work this out now. So what's going to be left in this integrand? First we plug in the 1. So this is going to be 3y plus 2y plus 3y squared. Then we can combine like terms after we're done with this, right? And then it's going to be minus, plug in the y squared. So this will be 3y to the 4th times y. So 3y to the 5th plus 3y to the 6th, right, plus 1, so 2y to the 7th there, plus 3 here, this is going to be y to the 4th plus 2, so y to the 6th. And that's that. And now we just very carefully combine all like powers. Really, the only like ones are here. We should distribute the minus sign, right? So the last thing here is go from 0 to 1 of, this is going to end up being 5y plus 3y squared minus 3y to the 5th minus 2y to the 7th minus 3y to the 6th. So you can change the order. Let's get them in numerical order. It doesn't matter, right? But we'll get them in numerical order here. 3y to the 6th minus 2y to the 7th then dy. So this one is just from 0 to 1. We just have to very carefully integrate this, and we'll end up with some terms in terms of fractions here, right? So we'll end up with 5 halves, just plugging in 1 and 0 as I go here. 5 halves plus 1, right? So plus 1, and then this is going to be minus a half minus 3/7 minus a quarter, and that's it. And then we just have to very carefully work out what this equals in terms of the fraction. So very carefully work this out, and what you'll get is 79 over 28. So just after some careful calculations, that's what you'll get here. So that's the answer to that integral. Hopefully we see now exactly how this is going to work, right? It works. It's very, very similar to integrals, double integrals, iterated double integrals, except there's a third integral, right? So you just have to do a little bit more work to find the region, a little bit more work to compute it, but otherwise it's the same type of work, right? So it's not much different. So here's another example. So for this next example that I want to work out, before we do the next example, I want to talk about a different type of coordinate system in three-dimensional space. These are called cylindrical coordinates, and these are not really that new. So the basic idea here is the following, and we'll talk about this again. We'll have another coordinate system at the end of this lecture. But in rectangular coordinates in three-dimensional space, if we have any point here, P, X, Y, Z, we know that the X, Y, and the Z represent the coordinates of the corner of a rectangular prism or a box, which that point lies on the edge of, right? There's another way to describe this point. There's actually many ways to describe this point. One way is to keep the same height, but then instead of thinking of the base down here as being the corner of a box, we can think about this base as lying, this point right here, as lying on a circle, right? A circle centered at the origin in the XY plane. And so this point right here, its coordinates are X and Y in terms of the rectangular coordinates, but its coordinates in terms of the polar coordinates on the base are R and theta. And so what we can do then is we can just describe our point up here, our three-dimensional point, by its polar coordinates in the XY plane, R and theta, and then its rectangular coordinate Z in the third dimension, right, in the Z direction. And if you think about that, the reason this is called cylindrical coordinates is because now this point doesn't lie, it still lies on the corner of this box, but instead of thinking of it as lying on the corner of a box, we can think of this point as lying on a cylinder, right, on a cylinder that sits directly above this point, right? So it lies on the cylinder directly above this point on the circle in polar coordinates down below. All right, so what that means then is that we can always convert at least in our mind, or in our point of view, we can convert from rectangular coordinates to polar or vice versa, right? We'll say cylindrical in this sense because now we're in 3 dimensions. And the transformation is going to be the following. So the transformation in terms of X, Y, and Z is going to be, remember this is called T of R, theta, and Z. This Z it's not a coincidence that it's the same letter, because it doesn't change, right? So our transformation is just that X is equal to R cosine of theta, Y is equal to R sine of theta, and Z remains itself, right? It's the same height here, same Z. All right, so we can compute these triple integrals in what are called cylindrical coordinates, and essentially it just boils down to working in polar coordinates in the XY plane and then Z, your regular coordinates in the Z direction. So one thing that I would like you guys to do, and I'm not going to work this out, but I will just state it here. So if you need to, pause the video here and work out this recommended exercise. But I'd like you guys to show that the Jacobian of this transformation, so the Jacobian of this is J. In this case, it's going to be J of R, theta, and Z, right? So it's 3 coordinates here. So it's three independent variables here, and the Jacobian of these is just going to be R. Okay, so that's what I want you guys to work out. So you take the partial derivatives the usual way, take the determinant of that matrix, and you should work out, it should end up being an R left over. And so what that means then, right, is that the dV, the volume element in cylindrical coordinates, is got to be Jacobian times dr, d theta, dz. So it's going to be R dr, d theta, dz. All right? And that's exactly what we would expect, because remember, the Jacobian of the polar transformation by itself is just R. We worked that one out together, so it's going to be very similar. It's just got this extra coordinate here. All right, so what I would like to do now is use polar coordinates to evaluate an integral that's given to us in coordinates that are not polar coordinates. So this is going to be item number 4 of our lecture. And I want us to evaluate the triple integral over region E of the integrand x squared plus y squared square root of the whole thing dv. So the integrand is the square root of x squared plus y squared. And then we need to know what E is again, right? So I've said this a few times, but these integrals don't mean much unless you're given, they don't mean anything really, unless you're given E, unless you're told what E is. So on this one, E is going to be the region. This is a 3-dimensional region, right? So E is going to be the region that lies inside of the cylinder. I'll just write the formula, but this is going to be a cylinder. So inside of the cylinder, x squared plus y squared equals 16, and between 2 planes. So between the planes z equals -5 and z equals 4. All right, so it's actually a pretty straightforward region if we're thinking in cylindrical coordinates, and I'll sketch it for us here. But the key here is going to be, when you do these on your own, is going to be to make sure that you decide that you think of, that you think in cylindrical coordinates. So the cylinder itself is just going to be on the base, it's going to be a circle of radius 4, right? So it's going to be a circle of radius 4 here on the base. And then it's a cylinder, so it just continues up here and down below. So there's the cylinder itself. Our region is inside of that cylinder, and it's bounded between 2 planes, right? So it's bounded between the planes z equals -5. All right, so we'll say that's right here, but z is -5. And then between the other plane is going to be up here, right? It's going to be bounded this way by z equals 4. And so our region is just the solid region that lies between these 2 planes and inside of the cylinder, right? Okay, and so this is our region E. So what we need to do is, before we even try to solve this integral, we need to write down what kind of region this is, right? Like, what are the bounds of this region? So we're going to use cylindrical coordinates. It's a cylinder, right? So cylindrical coordinates are definitely the way to go. And we can see exactly how this works, right? It's bounded exactly between. This is what you might call a cylindrical rectangle, which is a funny way to say it, right? But it's going to be bounded, but by just real numbers. So R is going to go from 0 out to 4. It's going to trace out in your mind. It's going to trace out from 0 to 4 this radius, and then I drew it in the wrong direction though. It's going to trace it out this way, right? Trace it out this way, and then we're going to rotate that around by theta, right? And so theta is going to go all the way around. This is the entire cylinder, so from 0 to 2 pi. And then z is going to vary from down here, right, and at -5 all the way up to up here, which is 4. So z just varies from -5 to 4. And now a couple things we need to remember. Our dv is going to be r, dr, d theta, dz. So we need that r. That's the key. And then the last thing is we need to change the integrand, right? So the square root of x squared plus y squared, that's going to just be r, right? Remember, x squared plus y squared equals r squared is the formula for r, the defining formula for r in the base. So this is just going to become r. And so now when we rewrite our integral, our triple integral over e of the square root of x squared plus y squared dv, this is going to become the integral from -5 to 4, integral from 0 to 2 pi, integral from 0 to 4 of r times r dr d theta dz. And this one is absolutely separable, right? And so let's see what we have here. This is going to be integral from -5 to 4 dz times integral from 0 to 2 pi d theta times the integral from 0 to 4 r squared dr. This one's going to be a breeze, right? So that's 9 times 2 pi times, this one's going to be 1/3 of 4 cubed. 4 cubed is 64, right? So this is going to be 64 thirds minus 0. So 1/3 r cubed, plug in 4, 4 cubed is 64. Okay, so this 3 will cancel here. And then if we work this out, 6 times 64 is going to be what? 384, I believe. So this is going to be 384 pi. Yep, okay. So there's an integral done in cylindrical coordinates. Again, the key here is just making sure you're organized. It's not really that hard at all, right? Making sure you're organized, sketching the region. The sketch doesn't have to be perfect. You just have to be able to write down your transformations here, your boundaries, right? And then your transformations, and then you go from there. All right, so very straightforward. So from that, we then go to another type of coordinates. So this next type of coordinates, these are called spherical coordinates. And it's a very similar idea to what we just described, except instead of our point lying on a cylinder, we're going to think of our point as lying on the surface of a sphere. So here's our x, our y, our z coordinates. Here's our point P, which has x, y, z coordinates here. All right, and so again, I'm going to draw this very lightly, but we know how this works, right? So there's the x, there's the y, there's the z components. I'm gonna try to draw lightly enough, and then that we can make sense of this whole idea here. So now the idea is that instead of lying on the corner of the box, like we've talked about, we want to think of this as lying on a sphere that's centered at the origin. So this is kind of, in many ways, more of a generalization of polar coordinates than the actual cylindrical coordinates are. So this sphere, this is the idea, right? So that point is going to lie on the surface of the sphere here. And my sphere is not drawn all that well, but this is the basic idea, right? So this sphere, the equation of this sphere, and the way that we're going to get our formulas here is this is going to be x squared plus y squared plus z squared equals rho squared, where then obviously rho is going to be the radius, right? So this is rho. So the length of that segment is rho. Now, to describe where this point is, we obviously need to know rho. We need to know the radius of this sphere, but we also need to know a couple different angles, right? And so there are a lot of different ways to determine which angles we want, but we are going to use the same ones as our text. And the text makes a decision to keep this angle right here, call it theta, in the xy plane, keep that angle exactly the same as it was for polar coordinates, right? So for polar and for cylindrical. So this is the same theta. This is obviously a different radius. That radius is rho. This radius down here, this projection down here, that's our radius r from our polar coordinates. That's not going to be one of the coordinates we need, but it's going to be useful in working out some of this other stuff, because the next thing we notice is that we have this triangle right here, right? These are all right triangles. But this triangle that has sides R, rho, and then Z, this side right here is Z. This is our old Z coordinate, right? This is our X coordinate. This is our Y coordinate. All right, and we know how those work. So X coordinate, Y coordinate, and then we have our Z coordinate here. The angle that we're going to use, the second angle, so the third piece of information that we're going to use here is going to be actually the angle that measures down from the positive z-axis downward right here. So this angle is going to be called phi. It's this angle right here, down here, right? But by similar triangles, that's the same as this angle right here. Okay, so that's the same as this angle right here. So now, with a little bit of very careful trigonometry, you can write out the formulas for this transformation. First of all, let's just write out what we know for sure, right? X and Y can be written in terms of R and theta. So we have the X is equal to R cosine of theta, and Y is equal to R sine of theta. But now we want to get everything else in terms of this angle phi and this length rho. So rho is the new radius, not R, right? R is not the radius. Rho is the radius, and then we want to get in terms of angle phi. So we can actually then use this triangle right here to write out, right triangle trig on this triangle to write out z and r in terms of rho and phi. Okay, so let's do that now. So in terms of z, this angle phi is the adjacent angle, right? And rho is the hypotenuse. So z is going to be equal to rho, it's supposed to be a rho cosine of phi, right? And then by the same argument, this is the opposite angle from side r. So r is going to be equal to rho sine of phi. And so now what do we do? Well, we're basically done, right? Because we have our formula for z in terms of rho and phi. Then what we have to do is just take our r and plug it in to these two equations here to get our x and y in terms of rho, phi, and theta at this point, right? Or rho, theta, and phi. Rho, theta, and phi. Okay, so rho, phi, theta was the right way to say it, actually. I should have left it that way. So here's what the transformation becomes. We get our x, our y, our z. They're equal to the transformation. Again, take some time, pause the video, and work out these formulas that I just wrote down. If you don't believe them, just do a little right triangle trig and get these formulas. But this is then going to be t of rho, phi, theta, in this order, okay? So I'm putting them in this order. Our text puts them in a different order. It changes the order of phi and theta. I want them in this order, though. But this transformation is going to be x is equal to rho sine of phi cosine of theta. All right. Y is equal to rho sine of phi, that's the r portion, times sine of theta. And then z is just equal to rho cosine of phi. All right, so this is our our spherical coordinate transformation. And just like with all of our other coordinate transformations, meaning our polar one and then our cylindrical one, this one does not move the point, right? The point does not move, but it will change how we measure the volume. And so again, as a recommended exercise, I want you guys to compute the Jacobian here. So compute the Jacobian. Compute the Jacobian of this transformation in terms of rho, phi, and theta. Again, in this order. So what is this going to be? This is going to be the determinant of the matrix that you get. So it's going to be dx by d rho in the first column. The next one is going to be dx by d phi, and then dx by d theta in this order, okay? And then we do all of them in the same order. dy by d rho, dy by d phi, dy by d theta, and then dz, d rho, dz, d phi, I wrote theta, dz, d phi, and then dz, d theta. Take the determinant of that thing, and what you should end up with, I'll write this down, but please pause the video, make sure you can work this out. It's very important. what you should end up with then is that the Jacobian of this transformation is r times rho, or the better way to say it is that it ends up being rho squared sine of phi. There's no r here, right? But in my mind, it's a good way to remember it, that it's r times rho, radius times radius. R times rho, but that ends up being rho squared sine of phi. So that's the Jacobian of the spherical coordinate transformation. And what that tells us, remember, the whole point of this is that then our volume element is given by rho squared sine of phi d rho d phi d theta. So there's our spherical volume element. This is the volume element that we get when we build our coordinates this way. And I need to give us some more information actually about the domain. So we need uniqueness, right? So up here, it's pretty, with our cylindrical coordinates, we're used to polar coordinates, right? So we know that r should be positive, right? So r should be greater than or equal to 0, and that theta should be between 0 and 2 pi, and usually with integrals you're not too worried about overlaps, but usually you don't include 2 pi, right? You just go 0 to 2 pi, and that's how you get unique coordinates everywhere except for at the pole in polar coordinates, right? And then z can be anything. Down here we need to make similar restrictions for rho, phi, and theta. And so the way that we're going to do it is we're going to have rho be positive. It obeys this relationship, and it's the radius of our sphere, right? So our rho is going to be non-negative. It's only going to be 0 at the origin. Everywhere else is going to be positive. All right. Then what we're going to do is we're going to allow our phi. So basically, how does this work? I'll choose a different color. I'll do this in orange because I don't have any orange on this picture yet. But basically, if rho is positive, then we think of that as measuring a positive distance in the positive z direction. So there's our rho. And then we're going to think of our phi as rotating outward, downward in the positive x direction from the positive z direction. So this is our angle phi. All right, and so that'll now trace out like a fan like this, right? So as it goes, it'll trace this out. But we only allow that to go from 0 to pi. So it can go from 0 down to pi, which is straight down, right? So phi is between 0 and pi. And then once we have that, then we can rotate all that fan that you end up with. We can rotate that fan all the way around in the theta direction to get to fill out the whole sphere at that point, right? So theta is then going to go this way, right? And as it goes, it's going to carry that whole fan with it, and it's going to trace out kind of a cone-like wedge, the way I've got this drawn here. But the idea, though, is that theta can go from 0 to 2 pi. Okay, and so that's the domain of our coordinates. So with, and it's very important, right, that our Jacobian depends on this choice that we've made. So we've made this choice. We're going to stick with this choice. So this is now our convention, that rho is positive, and we go in this order, right? Rho is positive. It traces up the vertical z-axis. Phi then opens down from the positive z-axis in the direction of the positive x-axis, and the furthest it can go, right, is to pi. So it could trace out a semicircle over here, right, or a semi-disk. And then to trace out everything else, then that disk can be rotated around all the way 0 to 2 pi in the theta direction to fill out the sphere. Okay, so that's our convention. All right, let's see how this works by doing an example. But again, make sure that you can compute all of this stuff yourself. So the Jacobian, make sure you understand how these coordinates work, the convention of these coordinates. All right, so this is going to be item number 6 in our lecture here. But here's an example. I'm going to give us this integral, -2 to 2. The bounds of the next one are negative square root 4 minus y squared to positive square root 4 minus y squared. And then the last one is going to be negative square root 4 minus x squared minus y squared, positive square root 4 minus x squared minus y squared. And then the integrand here is x squared z plus y squared z plus z cubed. And this is dz, dx, dy. We want to integrate this. We want to work out this integral. All right. Okay. So this does not look very pretty, right? It looks very complicated for our rectangular coordinates. All the pieces are a little complicated in their own right. So let's think about how this works, right? So this right here, if we just look at each of these, notice this is dz, and then we can write this out, right? So this one says that z is equal to, is plus or minus. So let's just look at the upper one. Z is equal to the square root of 4 minus x squared minus y squared. And this can be rearranged. We've got our minus one here, right? So this can be rearranged to say that z squared is equal to 4 minus x squared minus y squared, or that x squared plus y squared plus z squared is equal to 4. And this goes from the negative to the positive, right? So actually what we have here is that z squared, it's x squared plus y squared plus z squared is going to be less than or equal to 2 squared. So this means that it's bounded inside of a sphere of radius 2, right? And then we just need to check and make sure that the other boundaries correspond to the same sphere. And they do, right? So we can see then, if we just trace this out, sketch this out very tersely, as usual. This is a sphere of radius 2, right? So it goes, what this is saying is that we are supposed to integrate first in the z direction, right? So we integrate from this surface up to the top surface, right? So from the lower half of the shell of the sphere up to the top half of the shell of the sphere. And then once we do that, that collapses everything. So once you integrate in the z direction, it collapses everything to the xy plane. And now what are you left with? Well, now you're left with this disk of radius 2 in the xy plane, right? And so the next one says, okay, we're going to integrate that one in the x direction from the lower half to the upper half of the circle, right? So that one's going to go from back here. It's going to go from back there this way, right? To this side. So that'll integrate this. And again, once you integrate, you collapse. When you integrate, you collapse that dimension. So the x direction has been collapsed. And so the last thing left here is to go from -2 to 2 in the y direction. So this traces out the entire sphere, right? Now, how can we trace out that sphere obviously that means that spherical coordinates are going to be the right coordinates to use, right? Because look how complicated it looks in rectangular coordinates. But in our spherical coordinates, what are we going to do? Well, we're going to build this instead. Instead of building it the way that we just talked through, we're going to build this by first letting our row go from 0 out to 2. Remember how we said this works. It goes from 0 to 2 in the positive z direction. Then we're going to let our phi, so our phi is going to allow this arm here to rotate out in the positive x direction and down. So that's going to go from 0 to pi. Right? And so as that goes, it traces out this kind of fan-like shape. Okay? And then to fill out the whole sphere, right, instead of the way we built it here with all these crazy collapses, right, now to fill out the whole sphere, our theta is going to take that fan and it's going to rotate it around from 0 to 2 pi. So that will then fill out the entire sphere, right? So in the process, all of this gets filled in. And the picture doesn't look great, but the idea is the same. So that's the sphere. All right. We need, again, a couple of things. So these are our bounds. That's going to be a rectangle, right? So a sphere is a spherical rectangle. It's perfect, right? The next thing we need to do is look at the integrand or the volume element. Either one is fine, but we'll look at this one next. So this one is x squared z plus y squared z plus z cubed. This can be rewritten as z times x squared plus y squared plus z squared. Factor z out of everything. And then we notice what? That this z, is the formula for that is that's rho cosine of phi, right? For z. And x squared plus y squared plus z squared is another rho squared. So that means the integrand itself can be written as rho cubed cosine of phi, right? So that's our integrand now. And then the last thing we have to remember is that our dz, dx, dy, this is our volume element. This gets replaced by rho squared sine of phi d rho d phi d theta, right? So we put all this together then, and what we end up with is the integral. I'm just going to write I because I don't want to rewrite that whole integral, but the integral is now going to be the integral from 0 to 2 pi, integral from 0 to pi, integral from 0 to 2 of, put this all together, we have rho to the 5th power between the integrand and the volume element times cosine of phi times sine of phi. So cosine phi, sine phi, and then it's d rho, d phi, d theta. This one is separable again, so 0 to 2 pi d theta times integral from 0 to pi cosine phi, sine phi, d phi times integral from 0 to 2 rho to the 5th d rho. And then we just work these out, right? So this one's going to be 2 pi. This one, we can do there's a couple different ways to do this, but we could do this one by u sub, right? So the derivative of sine is cosine, so let sine equal u. Then cosine phi d phi is du. And then you just have to change the boundaries. But when you do that, look what happens. Sine of 0 is 0. Whoops. Sine of 0 is 0. Sine of pi is also 0. So that's 0, right? If that's 0, we know what's going to happen. But this one's then going to be 1/6, 2 to the 6, which is 32 thirds, right? But the whole point, since that was 0, this whole integral is going to be 0. So after all that work, we got 0. But the most important part of this was not actually the computing of these integrals. Make sure you can compute the integrals. That's obviously important. But the most important part was working through this change of variables, sketching, understanding, and then sketching the domain E, working through the change of variables, writing out the new integral, and then obviously the last step is to compute that new integral, which it turns out we got 0, right? Yeah. So we'll leave this lecture here. This is all examples of how to compute triple integrals, a couple new kinds of coordinates. Hope you guys enjoyed it, and I'll see you guys in the next one.